You're watching the screens. Everything has been perfect for months. 9 months of travel, hundreds of millions of kilometers, and every single check has come back green. Now the spacecraft is approaching Mars, the exact moment the entire mission was built for. The signal goes quiet. You expected this. The spacecraft is going behind the planet for orbital insertion, so you'll lose contact for about 20 minutes while the engine fires on the far side. Then it's supposed to come back around. The signal returns, and the science begins. You're watching the clock. Imagine the smell in that room right now. Stale coffee, the hum of computer fans, and the absolute crushing weight of 30 people holding their breath at once. The window for the signal to return opens. You're staring at that screen. Nothing. The window closes. Still nothing. You look around the room and you see it in the eyes of the person sitting next to you. Nobody wants to say it out loud, but everyone knows. You've just lost a $125 million spacecraft, and right now, you have no idea why. This was the Mars Climate Orbiter. It launched in late 1998 to be our weather satellite for the Red Planet. It was supposed to map the atmosphere and help future missions talk to Earth. For 9 months, the journey was textbook. The navigation team tracked it every day. They made small corrections to the thrusters to keep it on path, and the spacecraft did exactly what it was told. Up until this exact second, NASA thought they had a perfect mission on their hands. Here's the mystery that kept those engineers up for weeks. How does a perfectly healthy machine just vanish? It didn't blow up, it didn't run out of fuel, it didn't hit a rogue rock. To find out what happened, you have to look past the hardware and look at the numbers. Because the biggest failure in the history of Mars exploration wasn't a broken engine. It was a simple mistake in a spreadsheet. It turns out 2 teams were speaking different languages. The engineering team at Lockheed Martin, the folks who built the orbiter, were sending thruster data to NASA using imperial units, specifically pound-force seconds. But the navigation team at NASA's Jet Propulsion Laboratory was reading that data and assuming it was in metric units, Newton seconds. If you look at this diagram, you'll see the problem. Those 2 units are off by a factor of 4.45. For 9 months, every time the team made a tiny correction to the flight path, the spacecraft pushed back 4.45 times harder or softer than the navigators thought. It's like trying to bake a cake and confusing Celsius with Fahrenheit. The numbers look fine on the page, but the result is a disaster. It wasn't an obvious error. It was a tiny, invisible ghost in the machine. But over millions of miles, those tiny errors added up. By the time the orbiter reached Mars, it wasn't where it was supposed to be. It was way too low. Instead of orbiting the planet, it slammed into the upper atmosphere at thousands of miles per hour and burned up. You're probably thinking, how? How does a room full of the smartest people on Earth miss something you learned in middle school? But that's the trap of complex systems. When you have hundreds of teams and thousands of people working together, you have to make assumptions. You assume that if you're working at a science agency, everyone is using metric. It's so basic that nobody thinks to check it. It's like assuming the person you're talking to uses the same alphabet as you. You don't verify it because it feels impossible they aren't. This failure forced NASA to change everything. They didn't just fire people, they built a new system. They created a rule where every unit of measurement on every mission has to be independently verified by a second person, whose only job is to look for that mistake. That one change, born from a $125 million math error, has protected every rover and satellite we've sent into the void since. It's the reason we're on Mars today. The Mars orbiter was a machine, and machines can be replaced. But in April 1970, the stakes became human. Meet Jim Lovell, Jack Swigert, and Fred Hayes. They're 2 days into Apollo 13, heading for the moon. At this point in the 70s, moon missions felt almost routine. The news had mostly stopped covering them because, well, we'd already done it. It felt safe. It felt like we'd mastered the blackness of space. Then, 55 hours in, Jack Swigert flips a switch to stir the oxygen tanks. Suddenly, you hear a bang. Tank number 2 explodes, tearing a hole in the side of the spacecraft. Houston, we've had a problem. In the next few minutes, you're watching the telemetry and mission control, and it's a nightmare. 2 fuel cells are dead. Oxygen is literally bleeding out into the vacuum. The command module is dying, and 3 men are stuck in a tin can 2 days away from home, with no way to land on the moon. This is what mission control actually looks like when everything goes wrong. It's not panic, it's improvisation. They move the astronauts into the lunar module, using it as a life raft. But that creates a new problem: carbon dioxide. The filters are failing because they weren't meant to support 3 people for that long. The command module has spare filters, but they're square. The lunar module's holes are round. Imagine trying to save your friend's life by fitting a square peg in a round hole using only duct tape, a plastic bag, and a dirty sock. That is exactly what the engineers on the ground did. They talked the crew through building a MacGyver-style adapter, and it worked. Even then, the home stretch was terrifying. You're waiting for the re-entry, knowing that the explosion might have cracked the heat shield. If it did, the capsule would just disintegrate on the way down. You're staring at the clock during the radio blackout, waiting for any sign of life. Then you see the chutes. The capsule hits the water. All 3 men are alive. You can feel the room erupt through the screen.
We call Apollo 13 NASA's finest hour because the mission proved something more important than a successful landing. It showed that the collective brainpower of the team on the ground could solve a literal death sentence in real time. They took a total failure and turned it into a masterclass in survival. They didn't just bring back 3 men, they brought back the blueprint for how to handle a catastrophe. But space doesn't always give you a second chance to improvise. Sometimes the failure happens in the blink of an eye. In January 1986, the Challenger shuttle broke apart just 73 seconds after launch. 7 people, including a schoolteacher, were gone in an instant. You're watching the footage, and you see the plume of smoke split in 2, and the realization hits you like a physical weight. What makes Challenger so heavy is that it was preventable. The night before, engineers warned that it was too cold to launch. They knew the rubber O-rings in the boost ducts got stiff in the cold. Think of a garden hose that's been left out in the snow. It won't bend and it won't seal. They told NASA the rings would fail, but the decision was made to launch anyway. The rings didn't seal, the fire escaped, and the shuttle was lost because a warning was ignored to stay on schedule. 17 years later, it happened again with Columbia. During launch, you can see a piece of foam break off the fuel tank and strike the wing. Engineers on the ground flagged it. They wanted to use satellites to check the damage, but the request was shut down. The leadership assumed it wasn't a big deal because it had happened before without causing a crash. 16 days later, during re-entry, the hot plasma of the atmosphere poured through that hole in the wing and destroyed the shuttle. 7 more lives were lost. You look at these stories and you find a common thread that's scarier than any math error. Neither of these were surprise technical glitches. They were failures of human decision-making. It's what happens when the pressure to keep a schedule or stay under budget becomes louder than the engineers in the room. It's the belief that because nothing bad happened last time, nothing bad will happen this time. These disasters changed NASA's soul. After Challenger, we had the Rogers Commission. After Columbia, we had a total overhaul of the safety culture. They changed who gets the final say on a launch and made it so that any engineer, no matter how junior, can stop a mission if they see something wrong. They had to learn the hardest way possible, that in space, there is no such thing as an acceptable risk if you can prevent it. The truth is, every astronaut who sits on top of a rocket today is safer because of the people who didn't come home. Their legacy isn't just the missions they flew, it's the safety protocols that protect everyone following in their footsteps. We carry their lessons every time we light an engine. Roughly half of all missions sent to Mars have ended in failure. Half. Imagine if half of every car ride you took ended in a wreck. The Red Planet is a graveyard for human ambition. From the early Soviet probes of the 70s to the Beagle 2 and the Schiaparelli lander, the surface of Mars is littered with wreckage. But you shouldn't see these as signs that we don't know what we're doing. Mars is just that hard. To land there, you have to survive the 7 minutes of terror, where a spacecraft has to slow down from 20,000 kilometers per hour to a dead stop using parachutes and rockets, all while the computer does the work because Earth is too far away to help. Failure isn't incompetence. It's the only way we find the actual boundaries of what physics will let us do.
Every time a mission crashes, it gives us the data we need to make the next one work. Look at the Perseverance rover. It's currently rolling across the Martian dust, drilling for signs of ancient life. It's only there because of what we learned from the rovers that came before it, and the missions that never made it to the surface. We build our successes on top of our failures. To go into deep space, you have to be willing to fail. If you only ever do things that are 100% safe, you never leave the ground. The price of progress is the wreckage we leave behind on the way to the next great discovery. This brings us to the most dangerous mission NASA has ever planned, the first time we put humans on Mars. We've been preparing for this for 50 years, but the risks are unlike anything we've ever faced. Take a look at this signal delay. Because of the speed of light, it can take up to 24 minutes for a message to get from Mars to Earth. If something goes wrong on the surface, the crew can't call mission control for an answer. By the time the engineers in Houston even hear that there's a problem, 24 minutes have passed. By the time their answer gets back to Mars, nearly an hour is gone. Are we ready for that? Are we ready for the day when astronauts are standing on another world, staring at a failing oxygen tank, knowing that they are truly, completely on their own? Every decision they make will determine if they live or die, and nobody on Earth can help them in time. Every mission that's ever gone wrong has left something behind. Not just wreckage, not just loss, but knowledge. The kind of knowledge you can only get by trying something that might fail, and sometimes watching it fail, and going back to the drawing board and trying again. The spacecraft we're building right now, the missions heading to Mars, to Europa, to the edges of our solar system, they exist because of every mission that didn't make it. Failure isn't the opposite of progress in space. It's part of the price.